Hi friends, I am Snehal and today we are going to talk about the vertical circular motion. So, we are going to apply the law of conservation of energy to an object performing vertical circular motion and we are going to derive an expression for its minimum speed. So, let's begin. So, let's suppose that this is an object performing vertical circular motion. For an example, suppose this is a stone tied to a string and whirled in this vertical circle. O is center of the circle and R is the radius. So right now, suppose the object is at the topmost position. So what will be the forces acting on the object when it is at this topmost point? Obviously, there are two forces. One is the gravitational force F suffix g equals to mg, and since the stone is tied to a string, there will be tension in the string acting on the stone. So tension in the string is T. Now we know that for circular motion to happen, we need a force called centripetal force, which is directed along the radius and towards the center. Okay. So here we see that both of these forces, the gravitational force and tension in the string, they are directed along the radius and towards the center. That means they combined provide the centripetal force. So at the topmost point, let's call it point A, we have centripetal force F suffix Cp equals to the gravitational force F suffix g plus tension in the string. So we know that the centripetal force is given by mv squared over r. So we have mv squared over r equals to F suffix g, which is m into g plus tension in the string. Now we wanted to find out an expression for minimum speed of the stone. So the centripetal force has to be minimum. On right hand side we have m into g plus tension in the string. mg is constant, it cannot change. So it's the tension which can increase or decrease. So tension has to be minimum. And what is the minimum value that tension in the string can have? So minimum value for the tension is equal to 0. Alright. So for minimum speed, we have T equals to T min and that is equal to 0. So let's put suffix A over here because it is speed at point A. So we have mv squared mva squared over r equals to m into g. So m and m gets cancelled out and we are left with v suffix a squared divided by r equals to g, and that means va squared equals to rg, and therefore va equals to square root of r into g. So this is the formula for minimum speed in vertical circular motion in VCM at topmost point. Alright. So then we will use this formula for the minimum speed at the topmost point and the law of conservation of energy to find out minimum speed for an object performing vertical circular motion at any point. Now let's suppose that our stone is at any point P on this vertical circle and its position vector or the radius vector makes an angle theta with the vertical. So now we are interested in finding out an expression for the minimum speed of the stone when it is at this point P. Alright. So we can use the law of conservation of mechanical energy. The law of conservation of mechanical energy says that if object is acted upon by conservative force only, then sum of its potential energy and kinetic energy is constant. And here the conservative force is the gravitational force, and that's why the potential energy is the gravitational potential energy. So I can write that kinetic energy at point P plus potential energy at point P is equal to kinetic energy at point A plus potential energy at point A. So kinetic energy at point P is half of m into v suffix p squared plus potential energy we know from last videos that it is mg into h suffix p, because it is potential energy at point P, and it is equal to half of m into v suffix a squared plus potential energy at point A is mgh at point A. Then we can take this mgh suffix p on the other side. So we have half of m into v suffix p squared equals to half of m into va squared plus mgh at point A minus mgh at point P. Then we see that there is m in all the terms, so we can cancel it out and multiply with 2. So multiplying by 2, we get v suffix p squared equals to v suffix a squared plus 2 times. Alright, we are multiplying with 2, and I will take g common from these two terms. So 2 times of g into h suffix a minus h suffix p. Alright, then I will call this equation number 1. So in order to find out v, the speed at point P, we need to find out the difference between heights of points A and P. So let's do that. So now in order to find out the difference between heights of points A and P, we have drawn a perpendicular starting from point P on this vertical line, and suppose it meets the vertical line at point M. So we have difference between heights of points A and P equals to this distance. So I can write h suffix a minus h suffix p equals to this distance am, and distance am is equal to distance AO plus OM, and distance AO is nothing but the radius of the circle R. So we have HA minus HP equals to R plus OM. So in order to find out this distance OM, let's consider this triangle OMP. So in triangle OMP, we have cos of theta equals to adjacent side divided by hypotenuse. So OM divided by OP, and OP is the radius of the circle. So this is equal to OM divided by R. So we have cos theta equals to OM upon R. So OM equals to R multiplied by cos of theta. And then we can substitute it here. So we have HA minus HP equals to R plus R cos theta. So suppose this is equation number 2. Then from equation 1 and 2, we can write from 1 and 2, we have Vp squared equals to Va squared plus 2 times of G into R plus R cos theta. Alright, so we have substituted HA minus HP equals to R plus R cos theta in this equation number 1. So now for the minimum speed, VA should also be minimum because Vp depends on VA. So we have VA equals to square root of G into R. We know that minimum speed at the top is square root of G into R. So we can substitute that in this equation to get Vp squared equals to square root of GR squared is GR plus 2 times of G into R. I will multiply this out. So 2 times of GR plus 2 times of G into R into cos of theta. And then this is equal to GR plus 2GR is 3GR plus 2 times of GR into cos of theta. Then we can take GR common to get GR multiplied by 3 from here plus 2 cos of theta from the second term is Vp squared, and therefore we have minimum speed in vertical circular motion at any point is V suffix P equals to square root of GR multiplied by 3 plus 2 cos of theta. Alright. So now we have an expression for minimum speed at any point in vertical circular motion, and we are going to use it to find out minimum speed at these two special points, point C, the midway point, and point B, the point at the bottom. So we have at midway point, so point C, V suffix C equals to square root of GR multiplied by 3 plus 2 times of cos of theta, and for this point theta equals to 90 degrees. So theta is the angle between position vector or radius vector of the point and the vertical. So here it is 90 degrees, and we know that cos of 90 is equal to 0. So the second term becomes 0 and we are left with 3 times of GR. So speed at the midway point is square root of 3GR. Alright. And for point at bottom, so for point at the bottom B, we have V suffix B equals to square root of GR multiplied by 3 plus 2 cos of theta, and for this point the theta is 0. We can see that it's the angle between radius vector and vertical. So radius vector and vertical line, they are in line, so angle is 0. So cos of 0 and cos 0 is 1. So 1 multiplied by 2 is 2. So 2 plus 3 is 5. So we have V suffix B equals to square root of 5GR. So we found that minimum speed in vertical circular motion at the topmost position is square root of gr. Minimum speed at the midway point is square root of 3gr, and minimum speed at the bottom is square root of 5gr. And the formula for minimum speed at any point in vertical circular motion is this one. So v suffix p equals to square root of gr multiplied by 3 plus 2 cos of theta.